In this lecture, we will learn about Thevenin's theorem, and we will learn about it using a lot of actual solved problems, so you have a very good grip on this theory. To understand its importance, let's consider a very simple circuit. There is 36 voltage power supply, there is a resistor divider 6K and 3K, and then we have a load resistor connected in parallel with 3K, and we need to find out the current flowing in R for several values of this load resistor: 0K, 1K, 2K, 3K ohm, and maybe more. Maybe you have 10 different values and you want to find out what is the current flowing in this resistor RL for these different values of the resistor. So one way to solve using our college physics would be to use the Kirchhoff law. We have two loops, one this loop, another this loop, and using these two loops we solve two equations and find out the two currents. But then we have to repeat the whole thing for another value of RL, and then we need to repeat the whole thing for another value of RL, and so on and so forth. So Thevenin says that you can do some simplification so that you don't have to do it for all different values of RL. So how do we do that? So Thevenin says this whole circuit can be replaced by a circuit containing only the voltage and a resistor in series and this load resistor RL. If I could replace this whole circuit, this circuit could be very complicated. It can have 10 voltage sources, different hundreds of resistors. But if I could replace this whole circuit with just one single source of voltage and just one single resistor, then our life becomes easier. We can keep on changing the RL and calculate this value. We call it Thevenin, the Thevenin voltage source, and resistor has a special name called RTH or R Thevenin. Thevenin gave a method to calculate VTH and RTH. So we will do it one by one. First, in the first part, we will do Thevenin. What is Thevenin? How do we calculate Thevenin? So he says, mentally remove this resistor RTH from this circuit. So what we are doing is, we take this circuit and then keep this voltage source like this, keep this 6 ohm, the whole circuit as it is, just mentally remove these and name these two ends of the resistor point A and point B. This is 6K, this is 3K. And find the voltage across these 2 points. That will be the Thevenin's voltage that we will substitute in the circuit that we showed earlier. In other words, in practical life also, if you need to find a Thevenin's voltage, just if you can somehow remove the load voltage, just remove the part of the load and use a simple multimeter to measure the voltage across A and B after energizing your whole circuit. That will be your Thevenin's voltage. So what is the voltage here at VAB? This is 36 volt, this is 6K, this is 3K. You can use simple Kirchhoff law. There will be voltage drops on these two resistors in the proportion of the resistor value. Out of 36 volt will be divided in the ratio 6:3 or 2:1, which means 12, this will be 36 multiplied by 3 divided by 6, or 6:3, 3 divided by 9. So this is 4, this is 12 volts. So this is our Thevenin's voltage. We have found the Thevenin's voltage. So our Thevenin's circuit, and let us call it VTH. That we have found 12 volts. So that is the step number 1 in solving any Thevenin's problem. What is the step number 2? We have to find out the RTH. How do we find RTH? And for that Thevenin's give a rule that mentally short any voltage source. In this one there is only one voltage source, so we will short that voltage source. There is also a current source, because in electronics and in engineering we also have the concept of current source, which we don't read in college physics. Mentally short this voltage source, then the circuit becomes like this: 6K and 3K. And try to find out the resistance looking. Take these two terminals A and B, and if you have, in practical circuit, if you have a multimeter with you and use that multimeter to measure the voltage across these two terminals after removing this resistor, after removing your load resistor, that means it is the resistance looking into the circuit from this point. So if you have a circuit like this, these are two parallel resistors, 3K, 6K and 3K. Now you can find the equivalent resistance as 6K into 3K divided by 6K plus 3K. This will be 18 by 9K or 2K. So we have found, we write here as RTH equal to 2K. And what? Let's go back to our Thevenin circuit. Thevenin says that you can replace this whole circuit with a Thevenin circuit which has a voltage source as 12 volt and which has a series resistor of 2K, and then you can add your load resistor like this, RL. Now you can find out, it's easy if you keep on changing RL, and for that different values of RL you can find the current into it. For example, if RL is equal to 0, this implies the current into the circuit will be V divided by the sum of these two resistors is 12 volt divided by 2K plus 0K. This will be 12 divided by 2 or 6 milliampere. And then if I change RL from 0 ohm to 1 kilo ohm, in that case if RL is equal to 1K, this will imply that I will be equal to 12 volt divided by 2K plus 1K. 2 plus 1 is 3, 3 into 4 is 12, so this will be 4 milliampere. We can go on, keep on calculating something like this. I will do just one more for you. RL is equal to 2K. This implies I will be equal to 12 divided by 2K plus 2K is 4K, and this will be equal to 3 milliampere. So you see some brief glimpse of how the Thevenin's theorem is useful in calculating different values for different values of the load. But that is not, let's go on, move on to slightly more complicated circuit. The circuit is like this. So this is circuit. If you have studied about the Wheatstone Bridge, then this circuit, this is, let's say, point A and point B. If you have you have studied about the Wheatstone Bridge, and this circuit looks like a Wheatstone Bridge. So how does the Wheatstone Bridge work? This is a 12 volt source. This starts mentally, for example, mentally remove this RL from your mind. Let's take this RL away. And there is a current flowing in this loop, because of which it makes a voltage divider 6 volt. Half of this 12 volt is 6 volt and 6 volt appearing upon it. So this voltage will be 6 volt. And let's go to this loop. This is 6K and this is 6K, 3K. That means there is smaller voltage here and a bigger voltage drop here. These 2 points therefore are not balanced. It's not a balanced Wheatstone bridge. If it were a Wheatstone bridge, it's a balanced Wheatstone bridge. For example, this were 6K, this were 6K, A and B would have been the same potential. And there was no current flowing through this resistor RL. But we have to find the current in this resistor RL, and here the Thevenin's theorem comes to our help. If we could replace this whole circuit with the Thevenin's circuit, it will look like this: VTH, RTH, and then this is our RL. All we need to find out is value of VTH, value of RTH, and the rest of the thing will be simple. So let's start with VTH. How do we find VTH? To find VTH, what we do? We remove this RL from this whole picture. And we think this is 12 volt. We are trying to find out what is the voltage between points A and point B. And how do we do that? We can take this loop, and from this loop we see that this 12 volt is divided between 5K and 5K. So this point A is at a voltage 6 volt with respect to this point. If we look at this point, then if we take this loop and apply the Kirchhoff current law and then simplify these things, we'll find the current, and current multiplied by this 3K, we will find that the voltage at this point is going to be this 12 volt multiplied by 3 divided by 3 plus 6, 9. So this voltage will be 4 volt. That means V is at a higher voltage, B is at lower voltage, and VAB is equal to 6 minus 4 is equal to 2 volt. So we found in this Thevenin circuit, we have found VTH as 2.0 volt. So we are halfway, 1/3 way done. What is the next thing we have to do? We have to find out the Thevenin's resistance RTH. How do we find the Thevenin's resistor? We just need to short this 12 volt. How does the circuit looks after I short this? The circuit looks like this. $5K, 5K, 6K, 3K, and what we have to do, if we use a multimeter and measure the resistance between A and B, that will be our Thevenin's resistor. But there is a little problem. The circuit does not look very simplified. We need to re-simplify it to be able to calculate something like that. Remember, this point is same as this point, is the same as this point, is the same as this point. So let us try to rotate this 5 ohm here and rotate this 5 ohm here and join them like this. 5 ohm here, 5 ohm here, This is our point A, and from there, this is our point A. All I have done is, I have rotated these 2 points like this, and this is a simple copper. I have joined them here. This is this point, this whole copper point, joining from here to here. And now, from this point, I am joining this 3K. Now let us do this 3K kahega. I can join this 3K like this. If I rotate this thing here and bring it all the way on this side of this circuit. I have 3K here. In the same way, I can rotate this 6K over to here and bring it over to here, keeping in mind that this end of this 6K is the same as this point. So I have 6K here. And now if you carefully look, our B point rotates here and comes back here. Is that clear? If it's not clear, just try rearranging and thinking about it, and go back to this video once more and watch it. 5K and 5K are in, this is K, are in parallel, so this will be 2.5K. And 6K and 3.3K are in parallel, so this becomes this becomes 6 into 3 divided by 6 plus 3, 9. 3, this is 2. 3 into 2, 6, this is 2K. This is point B, this is point A. And sum of these two resistors will be 4.5K. This is our Thevenin's resistor. The resistor looking at these two terminals with the voltage source removed. RTH is 4.5K. So our problem now is reduced to, this whole problem gets reduced to a simplified circuit like this. And now if we are given that if RL is equal to 0.5K, we can find out the current into this circuit as V divided by R, 4.5K plus 0.5K, or 2 volt divided by 5 milliampere, or 0.4 milliampere. If I have made any calculation mistakes, you ignored it, but I hope you have got the concept into this. Let's move on to a little more complicated problem, slightly more complicated problem. So in this circuit, let us say you are required to find the current in RL for maybe 10 different values of RL, 0.5K, 1K, 2K, whatever. How do you do that? So once again, you need to put 1, 2, 3, maybe 4 different loops of Kirchhoff law, and then you solve it. You can solve it, but if I change the value of RL and find, hey, what if the RL is equal to something different? You again solve 4 different equations. You can do it with Thevenin's theorem very easily. But Thevenin's theorem also has a problem. If we try to find the Thevenin's voltage, we still have 3 loops. 1 loop, 2 loop, 3 loop. We remove this RL, we are trying to find a voltage across this, we still have a big loop. Our Thevenin's is probably easier because you can remove this, you can get that these two resistors are in parallel, become series, and then these two become parallel, this becomes series, and so on and so forth. But we have a slightly simplified thing, so I will redraw this circuit like this. I have drawn only a part of this. The circuit beyond this still exists. What we have done is, we are assuming that this circuit is the sum of this circuit plus this circuit. So this is our load. This whole thing is our load driven by this much of the circuit. I call it RL. Which means that I am trying to simplify the circuit by replacing this part of the circuit with its Thevenin's equivalent. So I write this whole circuit and I am trying to find out what is the Thevenin's. I am going to write the other part of the circuit also. 1K here, 2K here, 500 ohm here, RL here, like this. Okay, this is our circuit again. So mentally I break this. Okay, 2K is part of here. Mentally I am replacing anything beyond this with this is our whole RL, and I want to replace this circuit with a Thevenin's equivalent. How do I do that? To do that, I remove this thing and find the voltage on these 2 points. So what will be the voltage on these 2 points? It's 72 volt divided, this is a voltage divider. So 36 volt and 36 volt, this is an open circuit. So this 36 volt will appear here. That means this whole circuit can be replaced with the Thevenin's equivalent, which is 36 volt. And what is the Thevenin's equivalent resistance? So to do this, I replace this thing with a 0 ohm. So 2K, so it becomes like this, 2K, this is 2K, this thing is replaced by this short circuit, this is 1K. So 2K and this 2K are in parallel, 1K plus 1K is 2K. So Thevenin's equivalent series resistor is 2K. Now I connect the whole thing, whole of my load here back. So the circuit looks like this. 2K, 1K, 2K, 500 ohm, RL. Okay. So this whole circuit is simplified to one step to this, so I can remove this intermediate step. Now I can further simplify it, the same process. Let us consider these 2 points. And now this much is our load. And this is the circuit which we are trying to replace with its Thevenin's equivalent. So what we do to find the Thevenin's equivalent of this much of the circuit? We open circuit these 2 points. Then we open circuit this point, there is a voltage divider for 2K and 2K. So the Thevenin's voltage will be 36 divided by 2 is 18 volt. If it is not clear, just use it on a pencil and a paper and do it on it. To find the Thevenin's equivalent resistance, we short this voltage. When we short and look at the resistance from this point. So 2K and 2K are in parallel is 1K and 1K in series, this is 1K. So this is our Thevenin's equivalent circuit of this much apart. Now I put my back circuit back to 2K and 2K in parallel, 2K plus 1K, 2K in series, and this is the whole part of our load. This is our load, 500 ohm, and this is RL. So this whole circuit gets reduced to this gets reduced to this. Now we can proceed next step. I can remove this part. This again, now we have the final step. We are very close to our final step. This is our circuit driving this load. We want to find the open circuit voltage here. What it will be? This will create a voltage divider. There is no current flowing in this. So this 18 volt gets divided into 9 volt and 9 volt, and this is the 9 volt opening appearing here because the circuit is not closed. No current is flowing in the 500 ohm. So we have Thevenin's volt as 9 volt here. And what is the Thevenin's series resistor? We can find it by shorting this. I short this, I get a circuit like this. This is 500 ohm, this is 2K, this is 2K. So 2K and 2K is 1K and 500 ohm is 1.5K. So this is our RTH, this is our VTH. And we have a load resistor connected to here. Now you are required to find the current when RL is equal to 1.5K. And the current flowing in this one will be equal to V 9 volt divided by 1.5 plus 0.5 or 2K. This will be 4.5 milliampere. If I change this resistance RL, you can simply change this value of RL here and find the current load flowing into this. It's a ladder circuit. So it's not necessary that you apply the Thevenin's theorem to the whole of the circuit. You can do it in parts as much as you feel that you are comfortable with. So far in these problems, we had only one voltage source, but it is not necessary. You can have more than one voltage sources appearing in this problem. There may be a voltage source here, there may be a voltage source here, here. So let's do a little more complicated problem where we have more than one voltage source. So we have in this problem, there are three voltage sources trying to drive this RL voltage. We need to find out VTH, RTH, and finally the current in this load resistor. So I will have to use this space. So what I am first doing is I am removing this RL from this picture, and we are trying to find out the voltage between these points A and B. How do we do that? We will do a simple Kirchhoff law. Let us I1 current flows into this one. And out of this I1 current, I2 current flows into this. So in this one, we have a current of I1 minus I2. Now this I2 current flows in this one. We have open circuited this, so this I2 current also flows into this one. It comes here, there is no current flowing into this one, So the I2 current comes back here, and this I1 minus I2 plus I2, I1 current flows back into this one. We have one loop is this, another loop this, so we can solve. When you solve this, you write 20 volt. This 20 volt, let us say, is driving in this direction, because of which there is a drop of 2 I1 here, and then 4 times of I1 minus I2 on this one. So this is our first equation. Divide this equation by 2 and then simplifies. I1 plus 2I1, 3I1 minus 2I2 is equal to 20 divided by 2 is 10. This is our first equation. Now we will take this loop. This is one battery. It is minus 8 volt. It is against our direction of our chosen. This is minus 8 volt on the right hand direction. Right. You can follow whatever sign convention you like. Now the drops are 4I2 plus 2I2. This is 6I2. Minus, this is against our direction, so minus 4 into I1 minus I2. Divide this equation by 2 and simplify. On the right hand side we will have minus 4. 3I2 plus 2I2 is 5I2. And this is minus 2I1. These are the two equations we need to solve. In order to find the voltage across this, you need the current flowing through these resistors. So we need to find I2 and therefore eliminate I1. Multiply this equation by 2, this equation by 3, your I1 gets cancelled. And add these two. 15I2 minus 4I2 is 11I2 is equal to 20 minus 12 is 8. So I2 is equal to 8 upon 11. We found the I2. And its direction is positive, so it is flowing in this direction. Obviously, what is the next thing we need to do? We need to find out the voltage difference between A and B. What is the voltage difference will be? See, the current is flowing in this direction, and even though this battery is positive, that means this voltage will be higher than this voltage. That means A point will be even higher than this 4 volt. But what that voltage will be? We can apply Kirchhoff voltage law in this loop. So voltage between A and B will be equal to 4 plus IR, which is 2 into I2. 4 plus 16 by 11. This will be 60 by 11. This is the voltage at point A and point B. So we found the Thevenin's voltage. Let us write it here. VTH is equal to 60 by 11 volt. The next step is to find the Thevenin's resistor, and then we will be close to solving the problem. If you have confusion in this loop, go back to your Kirchhoff's notes, Kirchhoff's law equation, and try to solve it. The Thevenin's resistor is the resistance looking into this port when we have shorted all the voltage source. So how does the circuit look like after we have shorted all the resistors source? This is 2 ohm. This is shorted with this 4 ohm. This is 4 ohm. We have shorted this. This is 2 ohm. This is 4 ohm. This is shorted, and this is point A, this is point B. We need to find out the equivalent resistance looking from this point. This should be simple. 2 and 4 is 2 into 4 divided by 2 plus 4, 6. 2, 3 times 6 is 4 by 3. This is in parallel. So I can remove these two resistors and put a resistor of equivalent resistance 4 by 3 ohm. This is gone. 4 and 4 by 3 ohms are in series. So I can write 4 plus 4 by 3. This is equal to 16 by 3. So this becomes one single resistance of 16 by 3. Sixteen by 3 and 2 are in parallel. So 16 by 3 into 2 divided by 16 by 3 plus 2. Okay, so this becomes equal to 16 into 2 by 3. This becomes 3 into 2, 6. 16 plus 6, 22. 22 by 3, or you can write 2, 3 by 22. 3, 3 cancel. This becomes 11. This 16 by 11. So this and this is 16 by 11. 16 by 11. So we have a circuit like 4 ohm and 16 by 11. We can add these two. It becomes 4 plus 16 by 11. 4 into 11 is 44 plus 16 is 60 by 11. So our RTH is also 60 by 11. Now we have found the RTH with Thevenin's voltage and the Thevenin's resistor. What we need to do next? We'll just draw the circuit, equivalent circuit. Thevenin's resistor voltage, Thevenin's resistor VTH, RTH, and then this is our load resistor RL. And what is RL? RL we are given 8 ohm. So I will be equal to this voltage 60 by 11 divided by RTH 60 by 11 plus 8. 60 divided, we cancel 11 in 11, and 60 plus 88, 148. This will be 30 divided by 2, 30 divided by, or divided by 4, 15 divided by 4 into 3, 12, 2, 8, 15 by 37 amp. So this is the Thevenin's theorem. We have done all kinds of the problems that involve voltage and multiple voltage sources and resistors. But there is one more category of the problem which has importance in engineering. Probably for the physics point of view, it's fine. But physics, the practical electronics also have one more kind of circuit, and that is called the current sources. The Thevenin's theorem also applies to the circuit that has current sources. The current source typically it throws a fixed amount of the current using electronic circuitry. So let us consider a circuit like this. This is a current source of 3 amp. This is a resistor, let's say 10 ohm. And this is a 15 ohm resistor. And then there is a load resistor, we call it RL. And then this is how the circuit is. We need to find the equivalent Thevenin's equivalent circuit for this. That means, given this load resistor, replace this whole circuit with its equivalent Thevenin's voltage source and the equivalent Thevenin's resistor. So, to find the Thevenin's voltage, you have to first open circuit this thing and look into the voltage on these points. And that is what we are going to do. When we open circuit this point, this 3 ampere will flow and it will no more flow into RL. All this 3 ampere is going to flow in this loop. And when the 3 ampere current flows in this loop, the voltage across this point and this point V is equal to I into R. And R is 3 ampere, resistor is 15 ohm, so this will be 45 volts. A is at higher voltage, B at lower voltage. And this voltage will be called as Thevenin's voltage. The next thing we need to find it out is Thevenin's resistor. To find the Thevenin's resistor, we had replaced all the voltage sources with a short circuit. But if there is a current source, Thevenin says replace it with an open circuit, which means that we will replace this circuit like this and look at the resistance from this point. This is A, this is B. This is 15 ohm, this is 10 ohm. So when you look into this, you see that this is open circuit, so all the resistance you see is this one. Or if you can put an infinite resistance in parallel, which will have the same effect, that equivalent resistance of 15 ohm. So we can replace this whole circuit by its equivalent Thevenin circuit like this. This is RL, where V Thevenin is 45 volt and R Thevenin is 15 ohm, and RL is, let us say we need to find it for 7.5 ohm, and we need to find it the current for a load of 7.5 ohm. So I is equal to V by R. V is 45 volt, R is 15 plus 7.5, 22.5, 45 divided by 22.5 or 2 amp. So this is how you get the Thevenin's equivalent circuit when the circuit also has a current source. I will give you one more example that you can try it out, and if you're not able to do that, just leave a comment in the comment section and I may have some answer in another video for that problem if you are unable to do that. So the circuit is 12 volt, 6K, this is your load resistor. These are 3K resistors. These are all 4K resistors. You need to find out the current flowing for RL equal to 0 ohm, 1K ohm, 2K ohm and 3K ohm. And I'll give the answer for this. The answer is 24.7 microampere. V Thevenin, after you calculate it, V Thevenin should come out to be 4 by 27 volt and R Thevenin should come 6 ohm. try to see if your answer matches with this. If it's not matched, it may be my calculation mistakes as well. So make sure you leave a comment section if you see something not right with this problem, either with this problem or with the solution or anything else. If you like this video, I would like to make more about it. Similar to Thevenin's theorem, we have a Norton's theorem, another important theorem which has engineering and electronics application. Thank you for taking a look.